cis-Crotonaldehyde. Let us now study about the characteristics of aldol condensation. It is an irreversible change. It is an addition reaction with or without elimination of water. For example, aldol when heated produces crotonaldehyde. The new carbon-to-carbon linkage is set up. The aldols formed easily eliminate water to form unsaturated compounds. This reaction is characteristic of carbonyl compounds having alpha hydrogen atom. If there is no alpha hydrogen atom in the carbonyl compound, aldol condensation does not take place. Addition of hydrogen cyanide. Aldehydes and ketones react with hydrogen cyanide to form cyanohydrin. This reaction is carried out in the presence of a base catalyst. Now let us study about the mechanism of cyanohydrin. The step 1 involves the removal of the base, a proton, from hydrogen cyanide to produce cyanide ion. The reaction is as follows. When hydrogen cyanide reacts with hydrogen ion, it produces water and a nucleophile, that is nothing but Cn-. The cyanide ion attacks the carbonyl compound to form an anion, which is nothing but the step 2. Step 3 involves the proton from the solvent combines with the anion to give cyanohydrin. The H plus here reacts with the O here to form OH bond to result in the formation of cyanohydrin. Like other nitriles, cyanohydrin can be hydrolyzed to give carboxylic acid. When acetaldehyde cyanohydrin is made to react with water and heated, it produces lactic acid. This is a very efficient method of preparing lactic acid and other alpha hydroxy acids like mandelic acid. Next is about Grignard addition. Grignard addition to aldehydes and ketones are nucleophilic addition. The addition product formed is hydrolyzed to alcohols. Formaldehyde gives primary alcohol and other aldehydes give secondary alcohol with Grignard reagents. Ketones give tertiary alcohols. When formaldehyde is made to react with Grignard reagent, it produces a primary alcohol, that is ethyl alcohol. Whereas when acetaldehyde is made to react with the Grignard reagent, it produces an isopropyl alcohol, which is secondary in nature. When an acetone is made to react with the Grignard reagent and hydrolyzed, it produces a tertiary butyl alcohol. This is an example for the Grignard addition. This is a three-dimensional structure of urotropine. Addition of ammonia. Formaldehydes and ketones do not form addition products with ammonia. They yield the complex condensation products. Other aldehydes form addition products with complex structure. For example, when formaldehyde reacts with ammonia, it produces acetaldehyde ammonia. On further dehydrolysis, it produces aldamine. Formaldehyde forms hexamethylene tetraamine with NH3, as we can see here. This is used as an urinary antiseptic in medicine in the name of urotropine, and the structure of urotropine is as shown here. Benzaldehyde undergoes condensation reaction with ammonia to form hydrobenzamide. When benzaldehyde reacts with ammonia, we obtain hydrobenzamide, as we can see here. Acetone with ammonia forms acetone ammonia initially at room temperature. On heating, it forms diacetone amine. The reaction is as follows. Acetone on reacting with ammonia produces acetone ammonia. On high temperature and dehydrolysis, it produces diacetone amine. Reaction with hydroxyl amine. Aldehydes and ketones react with hydroxylamine to form oximes. Acetaldehyde, when reacted with hydroxylamine, produces acetaldehyde oxime. Aldehydes and ketones react with hydrazine to form hydrozones. Acetaldehyde, on reaction with NH2, produces acetaldehyde hydrozone, and acetone, when reaction, produces acetone hydrozone, as we can see here. Now let us study about the reaction with phenyl hydrazine, that is nothing but C6H5NH2. Aldehydes and ketones react with phenyl hydrazine to form phenyl hydrazones. Benzaldehyde, when reaction with phenyl hydrazine, it produces benzaldehyde phenyl hydrazone, as we can see here. Similarly, acetone on reaction with phenyl hydrazine produces acetone phenyl hydrazone. Reaction with semicarbazide NH2NH2CONH2, it produces acetaldehyde semicarbazone. Similarly, when benzaldehyde is made to react with semicarbazide, it produces benzaldehyde semicarbazone, as we can see here. The products of reduction depends upon the reagents used and the conditions of the reactions. Hence, a variety of reagents are used for reduction. Catalytic reduction. Aldehydes are reduced to primary alcohols by hydrogen gas in the presence of platinum metal as a catalyst. Ketone on catalytic reductions gives secondary alcohol. We can see here, when this ketone is made to react with a platinum catalyst, it produces secondary alcohol, and for example taken, it produces isopropyl alcohol. Reduction with metal hydrides. Metal hydrides like lithium aluminium hydride or sodium borohydride reduce them to alcohols. These are hydride ion donors. Hydride ion is a nucleophile, hence it is a nucleophilic addition reaction which is taking place. For example, when acetaldehyde is made to react in the presence of sodium borohydrate and H+ ion, it produces ethanol. Clemenson's reduction. Aldehydes and ketones can be reduced to hydrocarbons by zinc amalgam and concentrated hydrochloric acid. This reaction proceeds by electron addition to carbonyl carbon followed by protonation. Zinc metal is the electron source. In the absence of mercury, hydrogen gas will be evolved and the reduction is incomplete. This reaction is nothing but Clemenson's reduction. Now let us discuss about the reduction under strongly basic conditions. That is nothing but Wolff-Kishner reduction. Aldehydes and ketones are reduced to hydrocarbons by heating with hydrazine and sodium ethoxide. Hydrazones are formed as intermediates. The base removes the NH2 hydrogen atoms as protons, generating carbanion. Proton addition to carbanion gives alkanes. This is called as Wolff-Kishner reduction.